Hi and welcome back to the second topic of algebra. In the last video, we saw how we could solve for simultaneous equation. Extending this knowledge, we will be trying to solve for quadratic equation today, especially for equations which cannot be factorized out neatly. Furthermore, we will also be learning how to draw the quadratic function using a three-step procedure. Without further ado, let's begin. Where a variable is multiplied by itself once, such as x squared, the equation is said to be quadratic, a Latin word that means square. For any value of x that satisfies a given quadratic equation, we call it the solutions, also known as the roots. Often the general form is denoted by ax squared plus bx plus c equals to 0. The values that are tagged to the variable are also known as the coefficient, in this case the letters a, b, and c. Let us try to find the roots in the equation x squared minus 1 equals to 0. We can simply factorize it, and this will give us 1 and minus 1. This can be seen as the x-intercept when we graph the function out. The roots of any quadratic equation have a relationship with the coefficient of the same quadratic equation. This means that understanding this relationship would allow us to find the roots. Mathematicians often denote the roots of a quadratic equation by the Greek letter alpha and beta. If we take the sum of the roots, it will be equivalent to the negative coefficient of x divided by the coefficient of x squared. On the other hand, the product of the roots will be the same as the quotient of the coefficient of the independent term with the coefficient of x squared. As such, we can rewrite the general form of a quadratic equation as x squared minus the sum of the root x plus the product of the roots equals to 0. Let us take a look at the example. To solve for the quadratic equation 2x squared plus 3x minus 5 equals to 0, we may use factorization to help us solve. For illustration purposes, let us try to use the sum and product of the roots to help us find for the solution. The sum of the roots is negative 3 over 2, while the product of the root is negative 5 over 2. Using what we learned in the previous lesson, we can make alpha the subject in equation 1. Then, we can proceed to substitute this new equation into equation number 2. After expanding out the expression on the left, we can make one side to be equals to 0. In this case, we can move the expression on the left to the right side. To remove the fraction, we can multiply 2 across and then proceed to factorize. This will give us the 2 value of beta. These 2 value of beta are actually the roots of the solutions. If we substitute them to find alpha, we will get the same answer in reverse. This is because there can only be at most 2 values for any quadratic equations. Regardless, the roots are negative 5 over 2 and 1. Of course, we can easily find the solutions by factorizing the equation. However, in the event that a quadratic equation cannot be factorized out easily or has no real roots, then finding alpha and beta would be more appropriate. In school, you may encounter some of these expressions which can be easily rewritten using the identities. However, some students may not be able to remember these identities, and as such, here is an approach which you may want to consider. Let us say that you want to find the sum of alpha cube and beta cube. Looking at it, there seems to have some connection with alpha plus beta whole thing cube. So, we can expand out this expression as shown, and then simplify, and we will be able to see that there's an alpha cube plus beta cube on the right hand side. By moving the rest of the expansion to the left, we can make alpha cube plus beta cube the subject. As such, do not panic in the event that you cannot remember any of these identities. Let us see an example. We are first required to find the sum of the square of alpha and beta. Using the given equation, we can first write out the sum and product of alpha and beta. Then, we can proceed to find the required answer. As the sum resembles alpha plus beta whole thing square, we can expand it out and make alpha square plus beta square the subject. Then, by substituting the values into the equations, we will get 41 over 4. Next, for part 2, we can first combine the sum into a single fraction. In math, it is often easier to work with an expression that contains only one fraction rather than having multiple parts. As such, we can see that the numerator is simply alpha squared plus beta squared, and the denominator is twice the product of the roots. By substituting the relevant values, we will get negative 41 over 16 as the solution for part 2. With this information, we can proceed to the last part of the question. As we have found the sum of the new roots, we can now focus on the product instead. By multiplying it, we will get a quarter. As such, the new equation would be x squared minus negative 41 over 16 holding x plus a quarter equals to 0. Since we are required to present the equation with integer coefficient, our answer would thus be 16x squared plus 41x plus 4 equals to 0. Besides expressing the quadratic equation in the general form, we can write it in the vertex form by completing the square. This is helpful when we are trying to find for the turning point of the quadratic equation. There are two ways that a quadratic function can behave, and this is dependent on the coefficient of x squared. If the coefficient is positive, then the graph will resemble a smiley face. On the other hand, if the coefficient of x squared is negative, then it will be a sad looking face. Do note that it cannot be equal to 0, for otherwise the equation would become linear instead. Let us try to sketch the function y equals to x squared minus 1. To help us, we can employ the mnemonic should I turn around, or CETA for short. This stands for shape, intercept, turning point, and asymptote. Note that you may ignore the asymptote for now, as it will be more apparent in logarithmic, exponential, and trigonometric functions. As you are not required to know the definition of the term in your syllabus, some teachers may omit this term and only tell you that the graph does not touch a certain line. However, I have chosen to include this to make an easy reference. So, to sketch the graph, we know that the coefficient of x squared is 1. This means that the graph looks like a smiling face. We can then find the intercepts by making x equals to 0 and y equals to 0 separately. This will give us y equals to minus 1 for the y-intercept and x equals to plus or minus 1 for the x-intercept. Next, to find for the turning point, we can rewrite the equation in the vertex form. One way to do it is to expand the vertex form and make a comparison. Thus, by comparing the two equations, we see that 2h equals to 0 and h squared plus k equals to minus 1. This will give us h equals to 0 and k equals to minus 1, making the coordinates of the turning point to be 0, minus 1. We can then proceed to plot the three coordinates that we have found and sketch the graph. Earlier on, we learned that the coefficient of a quadratic equation can be used to find for the roots of the function. There is another method that can be used to solve for the quadratic equation. This is through the famous quadratic formula, which is written as negative b plus or minus square root b squared minus 4ac whole thing divided by 2a. Note that b squared minus 4ac is known as a discriminant, as it can determine the nature of the roots. If the discriminant is equal to 0, then we say that there is only one solution and the roots are said to be the same. However, if it's greater than 0, then there will have two distinct solutions. Conversely, if the discriminant is negative, then we will have no real solutions, as we cannot square root a negative value to get a real number. Using the quadratic formula, let us try to find for the roots of the equation x squared plus 3x minus 4 equals to 0. By substituting in the value of a equals to 1, b equals to 3, and c equals to minus 4, we will be able to get the expression negative 3 plus or minus 5 whole thing divided by 2. As such, we can conclusively say that the roots are 1 and minus 4. To summarize what we have learned today, quadratic functions contain a variable that is squared, and this can be expressed in two different ways, either the standard form or the vertex form. We also note that the solutions to a quadratic equation is known as the roots, and it has a relation with the coefficient of the function. This relationship can be expressed as x squared minus the sum of roots x plus the product of roots equals to 0. We also learned that the roots can be obtained through the quadratic formula, and the discriminant in the formula will tell us the nature of the roots. The vertex form, on the other hand, is useful to determine the coordinates of the turning point. This is especially important when we are required to sketch it out. Lastly, we can use a 4-step method to sketch the graph, and this can be remembered easily through the mnemonic "should I turn around."